part one of a little video on dealing with frames of reference and relative motion. And a lot of times we deal with relative motion just using common sense, and we're in pretty good shape. But sometimes um, the situation might be a little bit confusing, and it's nice to have something else to rely on. Okay? So let's take a look at a situation. Let's say we have a train here, and it's on the track, and then maybe there's a person in the train, let's say, and here's the ground, here's the train, and here's the person. I'll just put P for person. Okay? Let's say there's a ball flying through the air out here somewhere, maybe like right here. So there's a ball. And let's see if we can relate the ball's position to these different frames of reference. Okay? In physics, a lot of times we'll use an XY coordinate system. Oops, that's a Y there, sorry. X here. And this might be the coordinate system for the ground. So here's the ground's reference frame. And I can draw maybe another one for the train. I'm not going to draw a bunch. I'll just draw the ground and the train. We won't put the person in for this. And let's say the ball is, well, I drew it there, but maybe it would be up here or something. It doesn't matter. Here's the ball right here. The ball. Okay. Now, we're talking about position of the ball with respect to what. So it's very, very important to define what the position of the ball is in reference to. Okay? Well, the ball's position with reference to the ground can be expressed by this position vector right here. Okay? So we can just say, okay, this is the position vector of the ball with respect to the ground. So I put R for position vector. I know if it was in the X direction, we put an X there, or in the Y direction, we put a Y. But if it's diagonally, we usually like to put an R, and then a subscripts B and G. This is the position of the ball with reference to the ground. Okay? How about the position of the ball with reference to the train? Well, we'd look over at the train's frame of reference, okay, which would be over there. And from the train's frame of reference, the position of the ball would be like this, described by that position vector. So this would be like the position of the ball with respect to the train, with reference to the train. Okay? Now let's take a look at the position of maybe like the position of the train with reference to the ground. Okay, well, that would be like this, wouldn't it? Okay, position of the train with respect to the ground. Okay, so if we look at that vector triangle, we see that two of the vectors are touching tail to head, huh? We see the purple and the black vectors. The tail of the black vector is touching the head of the purple vector. So that should remind us of vector addition. And the red vector here, red position vector, is the resultant of these two vectors added up. So we could just write that down below in summary. The position vector of the ball with respect to the ground, RBG, is equal to the two vectors touch tail to head, right? So the position vector B with reference to the train plus the position vector of the train relative to the ground. Okay? And if you notice, there's something very interesting here. The inside terms here, the T on this one, and the inside T here, they actually, we can treat those as kind of a cancellation process. So we can cancel those out, and that leaves with RBG for our resultant. So RBG on this side equals RBG over there. So we're using basically dimensional analysis to tell us if we are doing this correctly. And since the t's cancel out and leaves us with RBG on this side and it's RBG on the left, we know that our process is correct. Okay? So that's kind of the idea. That's dealing with position vectors, right? But we could also relative positions. Okay, but we could also deal with velocity. You know there's a relationship between position and velocity. Velocity is the instantaneous change in position per time, right? So in calculus, if we took the derivative of both sides, we get dr dt on this side equals dr dt there plus dr dt there, and we end up with velocity of the ball with respect to the ground here is equal to the velocity of the ball with reference to the train plus the velocity of the train with respect to the ground. So what we have now is we have two formulas that help us deal with relative motion. One to help us deal with relative velocity, and one to help us deal with relative position, in that case of the ball. Okay? I'm going to turn the page now and we can get back to our train problem, one that's actually moving. Okay, so now let's say we have a train. Here's the train car. It's transparent on the side so people from the outside can see in. The train's moving. The velocity of the train with respect to the ground is, let's say, plus 50 miles per hour. Okay, let's say there's a person in the train, and the person is running toward the front of the train at plus 3 miles per hour. So I'll say that's the velocity of the person with respect to the train. And then we have the ground here. And we could have people standing on the ground watching the person through the transparent side of the train. So watching that person. And let's say we want to know the velocity of that person here, P, velocity of the person inside the train relative to the ground. Let's see if we can find that. Now this is something where common sense would help you, and you could do it without using the formulas that we had. Okay, but if you wanted to use that formula there, what would you do? We'd write it as velocity of the person with respect to the ground would equal the velocity of the person with respect to the train plus the velocity of the train with respect to the ground. And notice the inside term the t's drop off, it leaves with pg, which is we have on the other side. Okay, so let's go ahead and sub in. Oh, by the way, without doing that, what would the answer be? Not difficult, is it? Both the train and the person in the train are moving to the right, so they add together, and you're going to get 53 miles per hour. But let's just prove it using this relative velocity formula here. Okay, so velocity of the person relative to the ground would be equal to the velocity of the person relative to the train, which is a plus 3 miles per hour, and the velocity of the train relative to the ground, which is a plus 50 miles per hour. So we get 53 miles per hour as the velocity of the person as seen from ground level, seen from the ground frame of reference. Okay? And it would just be, if the person inside the train car was running the opposite way, it'd be negative 3. If they were running that way, it'd be a negative 3 miles per hour, whereas the train's going a plus 50 this way. And the velocity of the person with reference to the ground, in that case, would be velocity of the person with respect to the ground equals a negative 3 this time, plus 50, and that gives us a plus 47 miles per hour. So as seen from the ground, the person inside the train wouldn't seem to be running quite as fast as if they were running in the same direction as the train. Okay? So far so good. Pretty easy stuff. Okay. Now, what if we try a different problem? In this case, let's have a similar situation. We have the train. We have a person running in the train. The train's going, let's say again, train relative to the ground, plus 50 miles per hour. We have the person in the train, let's say this time running at the velocity of the person with respect to the train is equal, like say, negative 3 miles per hour. But now, let's say instead of ground frame of reference, we have a car here. Here's an automobile. Okay, so here's a car, and let's say the velocity of the car is going at, let's say, velocity of the car with respect to the ground is a plus 20 miles per hour. I forgot to put the units down for these, but you know what I'm talking about. Okay, so one question might be, what is the velocity of the person with reference to the car? Okay, so we got different frames of references. We have the train as a frame of reference. We have the ground as a frame of reference, and then we have the car as a frame of reference. We could that relative velocity formula could be used. I just had it using two terms, but you could have any number of terms here. In this case, we have three terms we have to add together. Okay, our first term we'd have to have with a p in front, so that'd be velocity of the person with respect to the train. Plus, now we need to get rid of the t, so we have to have velocity of the train with reference to something else like the ground. And then now plus the velocity of, we need something with a g in front here, looking at dimensional analysis, and then a c on the end. Notice that these two t's would be on the inside terms. They drop off. That'd give us the velocity of the person with respect to the ground. And then now we also have these two inside g's here would drop off, and that leave us with the velocity of the person with respect to the car. Velocity of the person with respect to the car. All the other terms cancel out. Okay, let's go ahead and plug our numbers in. Okay, the velocity of the person with respect to the train is -3 miles per hour, plus the velocity of the train with respect to the ground is a positive 50 miles per hour, and then plus the velocity of the ground with respect to the car. Well, there's the velocity of the car with respect to the ground, but how does that relate to the velocity of the ground with respect to the car? Because we just can't put a plus 20 in there. Well, it turns out that if you have these two letters switched, all you have to do is realize that they're in opposite directions. So the velocity of the ground with respect to the car is equal to the negative of the velocity of the car with respect to the ground. So that means all we have to do is say that velocity of the ground with respect to the car would be equal to negative of a plus 20, or just -20. Okay? So instead of putting a plus 20 in, since these g's and c's are switched, we'll put a -20 in for that. And so that's a -23 plus 50, and that gives us a positive, what? 27 miles per hour. Okay? And this is the velocity of the person as seen from the car. So this is the velocity of the person relative to the car. So that would be like somebody inside the car there looking at the person through a transparent window in the train and seeing that person running in there as if they were running to the right at 27 miles per hour. Oops, I had that off the screen, didn't I? Darn it. Okay. Anyway, so that's how that works. So we have 27 miles per hour. That's the velocity of this person inside the train as seen from somebody driving to the right at 20 miles per hour in that car. Okay, this is the end of part 1. Thank you very much.